Welcome to our exploration of artificial organs and the fascinating world of biomaterial surgical implants. Unlike a simple wound, where the body heals and the foreign object is eventually removed, biomaterial implants remain in the tissue for the long term. This ongoing presence means that the tissue must interact with the material in complex ways, setting the stage for unique biological responses. In this video, we'll delve into the materials, designs, and challenges of modern implants, starting with joint replacements and moving through vascular grafts and cardiac valves. Let's begin our journey into the innovations shaping the future of medical devices. One of the most common examples of biomaterial implants is the femoral stem and head, key components in hip replacements. The femoral head can be crafted from either metal or ceramic, and its surface finish may vary depending on the specific application and patient needs. These choices are crucial, as the interaction between the implant and surrounding tissue determines the success and longevity of the replacement. Selecting the right material helps minimize wear, reduce the risk of rejection, and improve patient outcomes. Moving to the acetabular components of a total hip replacement, we see further innovation in biomaterial science. The shell is typically made from metal, providing strength and durability, while the liner can be ceramic, metal, or ultra-high molecular weight polyethylene. Each combination offers unique benefits, balancing factors like wear resistance, biocompatibility, and ease of integration with the patient's bone. These design choices are at the heart of modern orthopedic surgery, aiming to restore mobility and quality of life. Total hip replacement is a marvel of modern engineering and medicine. By combining a metal shell with a carefully selected liner, surgeons can create a joint that closely mimics the natural hip in both movement and durability. The choice of materials is guided by years of research into how different substances interact with human tissue. This ongoing innovation ensures that patients receive implants that are both safe and effective, allowing them to regain mobility and live active lives. Let's turn our attention to vascular grafts, specifically the Advanta SSD. This graft stands out as the only PTFE graft that pulses and performs like a natural vessel, with minimal needle hole bleeding. Atrium's state-of-the-art membrane technology has resulted in a hydrostatic protection membrane that's both strong and supple. The proprietary trilaminate construction meets or exceeds all surgical and performance requirements, offering vein-like handling qualities that make it a favorite among surgeons. Hydrostatic protection membrane in the Advanta SSD is a breakthrough in biomaterial engineering. Developed and patented by Atrium, this membrane provides exceptional strength while remaining extraordinarily flexible. Its design ensures that the graft can withstand the pressures of blood flow without leaking, while also being easy for surgeons to handle. This innovation is a testament to how far biomaterial science has come in replicating the qualities of natural tissue. Trilaminate construction of the Advanta SSD vascular graft is a key feature that sets it apart. By layering different materials, engineers have created a graft that is both strong and flexible, able to pulse with the rhythm of the body. This construction not only meets all surgical requirements but also provides a handling experience similar to natural veins, making it easier for surgeons to implant and for patients to recover. Another remarkable advancement in artificial organs is the polyurethane cardiac valve. Designed to replace damaged heart valves, these devices must withstand constant motion and pressure. Polyurethane offers the right combination of flexibility and durability, ensuring that the valve can function reliably for years. The development of such materials has transformed cardiac surgery, giving hope to countless patients with heart disease. Carpentier-Edwards pericardial valve is another example of innovation in cardiac implants. Made from specially treated pericardial tissue, this valve is designed to mimic the natural function of the heart's own valves. Its unique construction allows for smooth blood flow and reduces the risk of complications. Such advancements have made heart valve replacement a routine and highly successful procedure. Design of artificial heart valves is a delicate balance between strength, flexibility, and biocompatibility. Engineers must ensure that the valve can open and close thousands of times a day without failing, while also minimizing the risk of blood clots or immune reactions. Advances in materials like polyurethane and pericardial tissue have made it possible to create valves that are both durable and safe for long-term use. Critical aspect of any implant is how the surrounding tissue interacts with the biomaterial. Unlike temporary devices, implants must coexist with the body for years, sometimes decades. This interaction can influence everything from healing time to the risk of infection or rejection. Researchers continually study these interactions to develop materials that are as compatible with the body as possible, reducing complications and improving patient outcome. Despite advances in biomaterials, the body can sometimes mount a foreign body reaction to an implant. This response, if fully developed, can compromise the function of the medical device, leading to pain, inflammation, or even device failure. Understanding and mitigating this reaction is a major focus in biomaterial research, as it holds the key to creating safer and more effective implants. When a foreign body reaction occurs, it can severely limit the usefulness of an implant. The body's immune system may attack the device, causing inflammation and scar tissue formation. This can lead to pain, reduced mobility, or the need for additional surgeries. By studying these reactions, scientists aim to design materials that are less likely to provoke the immune system, ensuring implants remain functional for as long as possible. Overcome the challenges of foreign body reactions, engineers focus on creating materials that are highly biocompatible. This involves careful selection of metals, ceramics, and polymers, as well as surface treatments that minimize immune responses. The goal is to make implants that the body accepts as its own, reducing the risk of complications and improving the quality of life for patients. Selecting the right material for an implant is a complex process. Factors like strength, flexibility, wear resistance, and compatibility with human tissue all play a role. Metals like titanium and cobalt chrome are popular for their durability, while ceramics and advanced polymers offer unique benefits in specific applications. The ongoing evolution of materials science continues to expand the possibilities for safer, more effective implants. Surface engineering is another crucial aspect of implant design. By modifying the surface of an implant, engineers can encourage better integration with bone or soft tissue, reduce bacterial adhesion, and minimize immune responses. Techniques like coating with bioactive materials or creating microtextures are just some of the ways that surface engineering is advancing the field of artificial organs. Longevity and durability of implants are critical for patient satisfaction and health. Materials must withstand years of use without breaking down or causing adverse reactions. Advances in both materials and design have led to implants that can last decades, reducing the need for repeat surgeries and improving overall outcomes for patients. Alongside advances in biomaterials, surgical techniques have also evolved. Minimally invasive procedures, improved imaging, and robotic assistance all contribute to safer, more precise implantations. These innovations help reduce recovery times, minimize complications, and ensure that implants function as intended for as long as possible. Ultimately, the goal of artificial organs and biomaterial implants is to improve patient outcomes and quality of life. By restoring function, reducing pain, and enabling greater mobility, these devices have transformed the lives of millions. Ongoing research and development promise even better results in the future, as new materials and techniques continue to emerge. Looking ahead, the field of artificial organs is poised for even greater breakthroughs. Researchers are exploring smart materials, tissue engineering, and even biohybrid devices that combine living cells with synthetic structures. These innovations hold the promise of implants that are even more compatible with the body, offering new hope for patients with complex medical needs. Conclusion: the evolution of artificial organs and biomaterial implants represents one of the most exciting frontiers in medicine. From hip replacements to vascular grafts and cardiac valves, these devices are improving lives every day. As science and engineering continue to advance, we can look forward to even safer, more effective, and longer-lasting solutions for patients around the world.